So good morning. Welcome to this morning's panel discussion, Materials Science and Where Do We Go Next? Real technology breakthroughs come on the back of materials development, but is there enough work being done to characterize material compatibility, and could this yield faster and more reliable results for manufacturers? I have two of Europe's key solder manufacturers here to discuss this with me. To my extreme right, we have Jost from Balver Zinn.
Yes.
Welcome, Josef.
Good morning.
And to my right here, we have Brian Craig from Indium Corporation.
Good morning to you, Trevor.
Good morning. So let me just start with my first question, which is in a smart factory environment, once technologists succeed in getting machines to communicate and operate intelligently, is the next step to characterize the material science?
Well, how about I have a go at that one, Trevor? So, material science is something that's driven us in the way that we develop materials for a long time. What I think we've got with the automated factories now is machines looking at what's produced at the end, making decisions on the machine prior to that to adjust the machine automatically. So that's what the communication between machines is doing.
Right.
The material fits into that with having a robust enough material design, which means that as those machines are doing the adjustments, the material's robust enough that it doesn't need, the machines aren't required to do those adjustments.
Right.
So have a wider process window and more consistent material, which eliminates the small adjustments the machines have to make.
Yeah, well, that makes a lot of sense, Brian, but I mean, clearly Indium Corporation knows a lot about how an indium solder will work with an indium underfill or other product. But what about other materials when you're using a board finish that you don't manufacture, you don't work with? I'm talking about how do we start and characterize that?
Right.
Joseph.
Yeah, it's the modern factory is quite a difficult manufacturing thing, because maybe that 1 minute you produce a board which has many difficulties, and the next second you produce another board which has no difficulties.
Right.
So the combination of materials, like which underfill was used before it goes through the reflow oven, or things like that, need to be posted on the barcode which goes with the material inside, no? So the machines have to identify which solution is going to be used at the end of the manufacturing of each part, no? So, because if the board is very complicated, maybe 7 layers, underfills, ball grid areas, or you have just 1 layer and only stickers, no? So, but this must all be identified in the beginning of the process, because then the machines have to be identified which are going to be used. Right. So I think the manufacturing in the future will be more machines with different applications and different users. And maybe the line is not one line. Maybe it has some, how you call this in good English, sight lines.
You have some different islands of specialty areas.
Yes.
That you work in. Yeah, okay. I see where you're coming from. But yeah, I mean, electronics generally are getting smaller. There's a lot of miniaturization coming in, a lot more electronics going into the automotive industry. The cars aren't getting any bigger, but we're packing more electronics in there.
Yep.
So the assemblies are getting smaller. Therefore, we're getting a lot more problems with CTE mismatches between these materials and different things. Should we be looking to trying to characterize material sets that work with each other to help the designers in the process?
Well, I think material sets has two sides to it. The material set, if it's well defined and fits the soldering material with the conformal coats or the board resist or the board finish, something like that, that makes the decision process much easier for the production line to be set up when it's first ready. They know what materials fit with each other. The other side to that is that if we only follow defined material sets, it reduces the innovation. So we don't have the experiment of trying what happens with material A, conformal coat B, underfill C, because it's not on that characterization list. I think the innovation is restricted a little bit.
In some ways, we're having to deal with that, though, in the field. I mean, for example, if you start to introduce a cleaning process into the manufacturing, you're having to go to a lab like at Kaizen to do all sorts of testing on coupons and various other things to see if you can get the cleaning material to work compatibly to remove the flux material from the board. So you're doing it after the fact.
Well, we do that before the fact as well, because when we develop a new material, solder paste, for example, one of the parts of that process is to use that material in our own internal PCB assembly type facility, but also work with the co-suppliers that exist in the marketplace today. So the board suppliers, does our material characterize with this board, this finish? Does it work with that cleaning solution?
Right.
And then produce with these people joint papers on compatibility with these materials. So that would be a normal part of our product development process, and it happens not just at the beginning of the product development, but throughout the lifetime of that product, because the chemical systems are constantly changing and evolving. So we have to stay on top of that as we develop materials.
That's true.
Actually, I would go a step further. Actually, we as solder manufacturers or chemistry suppliers, we love to be involved in the beginning of the product invention, no? Everything goes smaller and smaller, but there are physical characters which you cannot ignore when you want to produce a product which is going to be in a car built with vibration. Either whether it is a diesel or electrical, it doesn't matter.
Yeah.
So if we are not involved and we come to the point when the customer says, oh, and now we need to solder this, and we have to say, sorry, but there's a physical border which we have to cross. So we would have loved to be invited in the beginning of inventing this product. So we could give all our knowledge about materials, metals, and whatever is needed to create those products.
Right.
To be there in the beginning would be very, very nice.
Yeah, I would strongly agree with Joseph there. I mean, remember that solder is everywhere, absolutely everywhere. And why would you develop a new process without including the part that's everywhere right up front? And that makes absolute sense to me.
Yeah, absolutely. Yeah. No, well, I tend to agree. I like your feedback on that. But we need to looking forward. How do we start to extract data, reliability data, compatibility data from the line for manufacturers in a smart factory environment? I mean, at the moment we're doing it at the machine level. How can we do that to characterize materials going forward? Or are you suggesting that we do that before we start?
Well, as much as you can do before you start, the better. But if you think about a PCB assembly process using a solder paste, the characterization would be how consistent is that material over time. So obviously we know what it's supposed to behave like at the beginning, but as you use it, does its tackiness change? Does its wetting forces change? Does it begin to degrade through the printing process itself? Now, as I said at the beginning, the goal of people like us is to make sure that doesn't happen.
Right.
But how do we measure that and feed that back into the system so the machines are making adjustments? If the material begins to degrade in a process, then the way that you look at that is through your automatic inspection system. It will be finding that the print is degrading or there's missing parts or something like that, and it will make the adjustments in a connected production line to adjust for those parameters. Our goal is to make sure it doesn't have to.
Right, okay. So, looking forward to the increased miniaturization that's coming into the industry, are we going to end up having to use higher purity materials, and is that going to lay us open for other issues like tinned viscose more prevalent in the future?
Well, high purity materials is, you don't get away with being in this business for as long as we have by having low purity materials. So we're kind of there already.
Right.
I think the challenge is more about the miniaturization part.
Right.
So as we put finer deposits onto substrates and we put more and more tiny dots of material to join smaller components, we have to use finer and finer materials in size, in terms of dimensions, not in terms of purity.
Right.
And the big challenge, as we move from type 3, type 4, type 5 type powders into type 6, 7, 8, where no standards exist yet, no knowledge really exists, there's so many unknowns in that process that we have to characterize what's capable to be made, and organizations have to be able to help us define when it is made, how do you make it consistent?
Right.
So example, type 6, we have a number of definitions of type 6 inside Indium. Some have no lower limit, some have different lower limits. It's tiny material, very small.
Would you agree with that, Josef?
Actually, I totally agree, but it's getting even more complicated. You know, if we talk about type 6 powders for soldering materials, or type 7, there might be a corn which is just full of all these impurities, and the other one is the cleanest whatever.
Right.
And then we need to define how much flux medium we should have as a residue after soldering.
Right.
And the finer the powder is, so you need to protect the powder from oxidation before the soldering process. But how many flux is needed in the process, and how many flux residues are we allowed to have after the process?
Right.
If you talk about miniaturization, 1% flux medium residue in type 7 is, compared to this, maybe half a square meter.
Yeah.
If we have the type 7 powder, this is a square meter of flux residue. Do I need to wash? Do I need to remove? What is the... And this is why I agree. We need to be in the beginning of the process to help, to assist, to define the material and the residues or the cleaning process, whatever is needed.
Okay, okay. Super. So my next question is, what challenges is 5G going to bring you?
5G brings nothing but opportunity, in my opinion. But from a manufacturing perspective, what I love about 5G is it's more than just machines being connected and things like that. It's a massive enabler for us as human beings to do different things. And in our industry, we focus at two key areas. We focus at at least in Europe, we focus at the 5G infrastructure part of the business, and we also focus at the automotive electronics industry.
Right.
Those two industries are colliding like majorly at the moment.
Right.
And the 5G is an enabler that allows us to move from some driver assistance programs into fully autonomous vehicles. And what 5G does is it makes it safe, because as your car is autonomously driving along the street, it knows where every cell phone is, every lamppost, every bicycle, every shop, and so as it can make decisions to ensure that people stay safe.
Right.
And that's a huge thing, in addition to the fact that it knows how much milk you have in your fridge and when you have to go to the grocery store.
Well, I think it's an application. I think nobody would dispute the amount of benefit it's going to bring to us all in our everyday lives. But in the manufacturing process, what challenges are we going to get from 5G? Because a lot of these backplane boards and things like that, they're 9 kilograms or heavier. There's some real changes in technology coming about because of 5G.
Actually, 5G is going to change the world much more than we think now. Even in our production, in a solder manufacturer, where we have machines to produce bars and this and wires and this and that. So the connection between the machines and the order processing will be much easier for me as an enterprise, no?
Right.
But actually, there's one thing which maybe it's a little bit sarcastic, but maybe we can use 5G to chip also human beings, no? So it's easier to identify whether they are at work or at home.
Well, I think the Chinese are already doing that. I was there 2 weeks ago.
Don't get into politics.
No. They're using facial recognition to stop jaywalkers.
Oh, wow. No, but actually, this is where 5G is going to help us more. No, it will secure the world much more, because in front of a car, in front of a human being, in the moment is, does he brake or not brake?
Right.
After 5G, the car has break already.
Already, yeah, that's right. It's making the decision for you. Yeah.
From a manufacturing perspective, I think both these technologies are providing some manufacturing challenges as we squeeze more power into devices. Because
Right.
5G is a high power system. Automotive electronics is now, with the advent of more electrical driven engines, that's also a power system.
Yes.
And when you have a lot of power in a small space, you get a lot of heat. And it's so much of it is about ensuring that the solder joints that you make are going to conduct that heat out of the important parts of the process very quickly. So that means low voiding, that means thermal interface materials that are hugely reliable over a long period of time. And those are key challenges that they're not new, but they're becoming continuing key challenges as we put more electronics and high power into smaller spaces.
Yeah, very true. Okay. Well, gentlemen, looks like we've got lots of challenges ahead of us, that's for sure.
Always.
For sure.
And challenges, of course, also transmit into opportunities. But I want to thank you both for joining us today and discussing this. Josef Jost from Balver, Zinn, and of course Brian Craig from Indium Corporation.
Very welcome. Thank you.
Thank you very
gentlemen.
much.
Okay, and thank you for joining us today.